Alright, hi everyone, welcome to our new lecture. So I haven't been teaching for quite a while actually, probably it went like 4 days I think, 4 days or 5 days, I'm not sure. But it has been quite a long time since I last taught. So I decided, you know what, just shrug it off, who cares, I'm going to teach again. Anyway, so this will be our first lecture after maybe 4 days later, 5 days later, I'm not sure. I did teach, it's just that I forgot to publicize on YouTube. So let's begin with section 2.5. So that will be our bound state versus scattering state. So this section will only consist of bound state, not the scattering states, but only the bound states. Because yeah, sure, I could do all of it, but do the bound states, but just understand that for that alone took 1.5 hours to understand. So obviously, what do we know about the bound state? What do we know about bound state? Simply put, bound state found in system like it's found in systems like the infinite square well, or you call it the infinite potential well, and we have the harmonic oscillator. So in most cases, in cases like infinite square well, or what is sometimes called infinite potential well, and the harmonic oscillator, we can find the bound state, the rules of bound state applying these conditions. And we know that the equation for it would be plus infinite minus infinite psi of x squared dx would be 1. So this means that the probability that this means probability that particle will exist from minus infinite to plus infinite is 1, defining that the probability that the particle will exist from minus infinite, from anywhere between minus infinite and plus infinite, is always 100%, 1. Right? But what does this mean physically? Physically, we say that because 100% the particle will exist, I can say that sure, particles are trapped. And they're trapped as wave motion, so like wave particles, which means you can have like, so 1 2 3 4 5 6 to 7 nodes. So 7 nodes, you can have 2 nodes, you can have 3 nodes. But main thing is two things. One, the particles are trapped. Particles are trapped inside the wall, which then leads us to configure that the energy is less than the potential. Right? The energy is less than the potential, the total potential. Not the minimum potential, the total potential, like the overall potential. Energy is less than that, because if energy is more than that, then these particles would have the opportunity to also escape. But if it has that opportunity to escape, this means I would have to actually calculate the math for this guy and the math for this guy, which gets way too complex. Maybe we explain that, maybe we won't, but we'd have to do two different equations for that. But because we know that in two things, in one, the particles are trapped inside the wall, which then leads to the energy of that specific particle that's moving as waves less than the potential. The only equation that I have to actually really focus on is the normalization equation itself. And two, these are n is discrete, not continuous. So now if I were to represent that, I can represent it in summation from n equals 1 to, let's say k from, no, actually, right, n equals 1 to n, and I would have c of n sin of x e to the power minus either e n of t by h bar. So I would say in n format with each n discrete values with n each discrete values. Cool. Now, bound state, a little bit description is done. So let's move on to scattering state. We're not done with bound states. Bound state, only the base explanation is done. The math part we haven't touched yet. Only the base explanation is done. And for the scattering state base explanation, these are mostly in the free particles or any particle that encounters a potential barrier. But the famous one is the free particle, which we have done in section 2.4. I have not recorded section 2.4, so I'm actually going to record section 2.4 after finishing section 2.5 because one, I have a midterm, so it's best for me to revise, teach, and do the questions and stuff. It's actually good for me. So it's best that I do 2.5, then I'll do 2.6, then I'll go back to 2.4. Cool. So we have a free particle here, right? Free particle. This is like the famous one. And now if I were to integrate psi of x squared dx, it'll be infinite. Why would it be infinite? Because they are free particles, they're not restricted to anything. Because they are not restricted to anything, I cannot jail or I cannot trap a free particle. A free particle potential is never zero, so it is able to move. The potential is able to move. This allows us to say that the potential will be infinite. It can move anywhere. It doesn't have to, because there's no walls in it. So you can say there are walls, like wobbly walls. So it can go out, it can move anywhere. It's free. The world is the world. The open space is the particle's playground. So it can move anywhere. So it's infinite. But it's not one, right? And the only reason it is infinite is because these particles are somewhat affected by the potential. So in a free particle, potential is never zero. It is always continuous. Because the potential is never zero, unlike in the infinite square well. And now, if I were to derive it in my Schrodinger equation, I won't be able to derive it. And the reason I won't be able to derive it is because if I were to write the Schrodinger equation, which is minus h bar square upon 2m d square psi dx square plus v psi of x. If I were to derive this, it's going to be infinite psi of x. Right? It's going to be infinite psi of x because it's moving everywhere. But I cannot do that. Instead, I know that constant equation we did, that k is equal to root of 2me upon h bar. Right? And then from there on, we know that minus h bar square upon 2m d square psi by dx square, and we know that so d square psi by dx square plus v psi is equal to e psi, and then we did the substitutions of 2me by h bar, so minus 2me by h bar square, so we had d square psi by dx square is equal to minus 2me by h bar square psi, and then we know that k is root of 2me by h bar, and then now if I were to square this, I would leave it as minus k square psi, right? Now in a bound state, you do not write summation like you write in a boundary state. In a free state or a scattering state, you don't write summation. The summation only works for discrete values. So it only works for certain values, like 1, 2, 3, 4, 5, and so on. Only discrete values. You see, when you sum up values, you don't sum up all the infinitesimal points. You sum up one box plus one box plus one box. So each box you're adding. Now you see, a box is never 1.1. The dimension of a box can be 1.1. But you don't say 1.1 box. You don't say that. Summation is like adding each of those boxes. So this would be C1 psi of 1, and inside this, so this box is labeled C1 psi 1, and inside C1 psi 1 I have some attributes, some specific attribute, and then C2 psi 2 has some attributes, C3 psi 3 has some attributes, C4 psi 4 has some attributes, but they're discrete. And so each of those boxes contain 1, 1, 1, 1. But if I look at the scattering part, it can be anywhere here, 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 it can be anywhere here. Now you see, this dimension does not necessarily have to be 1. It can be 1.3, it can be 1.4, it can be 1.5, any. But obviously I am not going to use a continuous variable as my summation. It's like saying I'm going to add 1.1 box plus 2.3 box plus 3.3 box. You don't say 3.3 box, you say 3 boxes, right? But in a scattering state, it's not in terms of boxes, it is in terms of a position, which can be a real value. And so this is why we integrate minus infinite to plus infinite. We typically don't say minus infinite to plus infinite. We usually say minus epsilon to plus epsilon, but we're going to explain that later why. So we'll have C of k, I'm going to say k because n is for the discrete. C of k psi k of x e to the power minus iota ekt by h bar dx. This allows us to calculate the total, whatever the value is, whatever the value could be at every infinitesimal values. Every infinitesimal values, I am able to add all those infinitesimal values and get a value. Cool. Now, moving on. Let us recap a bit about the infinite square well, because there is a specific notation and why I use that notation, why the book also used that notation. I'm going to explain that. But before that, let's just jump a bit into the infinite square well. So infinite square well. So what do we know about the infinite square well? Obviously inside the one. Inside 1, my v of x would be 0, and outside 1, my v of x would be plus infinite. Plus infinite, minus infinite if it's on the left hand side, plus infinite if it's on the right hand side. However, this is for an infinite. The keyword here is what? Infinite square well. What if it was a finite? So what would I do to make it finite? Sure. How can I go from infinite to finite? What would I exactly do to allow it to move from infinite to finite? Infinite to finite. I would have to shrink it. Now if I shrink it, then shrink it again, then shrink it again, I'm creating it finite, right? But why did I say shrink 3 times? I'm going to explain that in a second. Now let's say I shrunk it from 0 to some value a, right? Because I shrunk, this means I lost some space. I lost, right? So now my v of x would be minus v0 for absolute value of x greater than less than a, and for 0 for x greater than a. Now why did I go for minus v0? Right? You can ask this question, why did I go for minus v0? The reason I went for minus v0 is because I shrunk. Inside the potential well, inside the potential well, if it was an infinite, it goes from minus infinite to plus infinite. Not 0 to infinite, it goes from minus infinite to plus infinite. Or maybe in this case, if you want to only, because saying minus infinite to plus infinite, it's like a double-sided, right? So you can say 0 to plus infinite or minus infinite to 0. They mean the same thing. They mean the exact same thing. So we're going to say 0 to plus infinite. So from 0 to infinite, it is an infinite square wave. So inside this wall, my potential is 0, right? Because honestly, I don't care. I don't give a shit about the potential. Why would I give a shit about the potential? My length is infinite. It's like saying I have billions of dollars, but I'm spending what, $10,000? Like who cares that I'm spending $10,000 when I have a billion? Right? You get the idea, right? But now I shrunk it. So now I'm limited. But because I shrunk, so I know that the space that I lost, so I'm going to feel something. I'm going to be aware that, okay, I shrunk. So now I'm going to get some potential. Now I'm going to get some attraction. I'm going to get some awareness. Because here, there's no awareness. In the infinite square world, there's no awareness. It's like saying you have $1 billion, but you're going to spend $1,000. Who cares about you spending $1,000 when you have $1 billion? Now, let's say it shrunk to 250,000 and you're going to spend 10,000. If you are good with your awareness or whatever, you can be like, okay, I'm spending $10,000. I have $250,000. So I'm shrinking a little bit. I'm being a little aware now. So I'm going to feel some potential, which I'm going to draw later. I'm going to feel some potential, right? I'm going to feel some potential, surely. This feeling potential, and the only reason I'm getting a negative, it is a positive, but because I'm shrinking it, I'm losing space now. So I went from here, I'm going to draw a dot, dot, dot. I'm going to draw this, and I'll end up here. So you see I lost some space. So because I lost, it's like a subtraction. So it ends up negative. Right? Because if it was a positive, I'm occupying more space. So it goes from more than infinite, which is no need. I'm already at infinite. Only option I have is to shrink it. But if I shrink it, it ends up negative. Cool? Alright. Now, remember I told you about the attraction part? Like you feel some awareness? This is where you get some awareness. I'm going to write x equals 0 here. Now, at x equals 0, what happens is it's going to stay at 0 and then it's going to go up. It's going to go exponential upwards. After all, it is an exponential curve, right? So it's going to go all the way up. So what I'm going to have is that wall over here, this section here, I am going to have some infinite point, like infinite end point, right? But one question is that I'm only getting for this guy here. I'm only focusing on this guy. Obviously, I'm going to focus on this guy here. Why not? Because at x equals 0, it is infinite. Everywhere else, it is 0. But if everywhere else it is 0, but only that specific section is not 0 but infinite, how can I keep it balanced? Meaning, how can I satisfy this rule or this attribute that x equals, so like that my wave function will be infinite at x equals 0? How can I meet this attribute here while keep these two attributes same? So meaning I have to find an equation such that this attribute is met, where it will be infinite at x equals 0, and the attribute for these two are met inside the same equation. Now I think I forgot to mention one thing. I kind of forgot to mention one thing. I did, right? Yes, I forgot to mention one thing. Where did it go? Ah, yes. No, I didn't forget. Okay, now the question is, if it at x equals 0 is like pooling. So at x equals minus infinite, it's shrinking, shrinking, shrinking. I don't see anything, I don't see anything. The minute it hits 0, it's going to pull that. It's going to literally grab that and pull it up. At x equals 0, it's going to literally pull it up. Now, how does this attraction even occur? Where do we get this equation that allows this attraction, and on top of that, these sections are met, these two sections are met? How do we even do that? Mathematically, we can derive it in the form v is equal to minus alpha c of x. This is not integration, this is c. Okay, let me write this c properly. Minus alpha c of x. Now this equation gives us an insight into how the potential will behave at x equals 0, at x equals 0 from the left, at x equals 0 from the right. And in general cases, I am not going to have this equation. Because if I were to write this equation, if I were to write the Schrodinger equation, so if I were to write the minus h bar square upon 2m d square psi by dx square plus v psi of x is equal to e psi of x, and now this v psi of x, I know what the equation is minus alpha c of x. So minus h bar square upon 2m d square psi by dx square plus minus alpha of x c of x psi of x is equal to e psi of x. Now this guy will end up 0. Why is it 0? Because at x equals, I'm not focusing on x equals 0 now. I know what my value for x equals 0 would be, but it diverges. What's the point? It diverges, correct? It goes to all the way to what? Infinite. What's the point of even focusing on that goal? We focus on the ones from, it's like, you did in calculus 1, instead of focusing on 0, you go from 0 from the left and 0 from the right and match that value until it comes to that point. Remember, you did that in calculus 1. So what we are doing is that we are not only we're going to focus at psi of 0 from the left and psi of 0 from the right. So we're going to focus on these two sections. But in these two sections, if it is not x equal to 0, the entire thing is gone. It's gone because it is not x equals 0. Even if it is x equals minus 100, it is still 0. The only time this, some air, we call it air, that contains this quantum mechanical attributes will pull that. So if let's say your graph, and this is one magnet. This magnet will actually pull the minute that particle that's coming as wave will come as 0, then it's going to attract, it's going to go down again, and then it's going to go 0. So it's for a millisecond. Remember we did the wave function collapse? This is like a bigger description of it. This wave function collapse, like goes, and it's going to attract so high, like it's going to attract so quickly for a millisecond, and it's going to go down again and then go back to 0. It's like direct. It is direct. Right. Now what? Now that I know there is 0, I end up having minus h bar square upon 2m d square psi by dx square plus 0, which is equal to e psi of x. Now typically I can denote this in the prime notation, which is psi prime prime, or I'm going to have minus h bar square upon 2m psi prime prime is equal to e psi of x. We good, right? We good. Okay. All right. All right. What do we know about the bound state? Given we're still in bound states, what do we exactly know about bound states? I know that E is less than 0, right? E is less than 0. Why is E less than 0? E is less than the potential, that's the norm. But the potential here is 0, so typically E is less than 0, right? And because E is less than 0, what do I know about my potential equation? No, not potential, the energy equation for the bound state specifically. What equation do I know for the energy, the conserved energy? I know that E is equal to minus h bar squared k squared divided by 2m. I also know what? Minus h bar squared upon 2m psi prime prime is E psi of x, or E, right? So what do I have? I have two equations here. Minus h bar squared upon 2m psi prime prime of x is equal to minus h bar squared k squared divided by 2m psi of x. These are my two equations because this is E, this is also E. What can I do? I have a minus a cut it off, h bar square cut it off, 2m cut it off. So psi prime prime of x will simply be k square psi of x. Psi prime prime of x is what? Simply what? K square psi of x. Then when we try to integrate this shit here, what do we get? We get a e to the power kx plus b e to the power minus kx, right? Or you get a sin kx plus b cosine kx, right? Now, we're not done yet. What is it? Now, if I go back to this graph here, where is it? Here. So if I go back to using the potential again, I know that for the bound state, we're still at bound state. If I were to use this potential, so if I were to use the time independent and the wave equation, and I know that v of x is minus alpha c of x at x equals 0, it is going to go infinite. Sure. At x equals 0, it is going to go infinite. So my psi of x or psi of 0 would be infinite. Cool. Psi of 0 would be infinite. But what is the problem here? On our equation, in order to find a delta function, or if I were to find a wave function, because what's their equation? Minus h bar square upon 2 and psi prime prime. So this means I would have to find the second derivative. But to even find the first derivative of this, so let's say this is my curve. This is my curve. Now, what do we know about first derivative? First derivative technically is the change between the 2 points. So this will be my first derivative. This will be my second derivative. So first derivative is a zoomed in image of the original image. But if you look at the difference between these 2 points, they're extremely high. So this is like 1, this is like 10,000. So you see the difference is high. And because psi prime difference is so high, it is not smooth. Now yes, this is not how the graph looks, this is how the graph looks. So now yeah, you may ask, find the difference for these two. You see that this is 0, this is 0. Only at x equals 0 will there be a change. Not at x equals 0.1, not at x equals 0.2, at x equals 0. So at x equals 0, it's like this. So if I were to find the point for this guy and the point for this guy, it is way too high. The difference between the 2 points is extremely high. So what can I do? What exactly? Okay, I can't find the first derivative. I can't find the exact value. I can't find the exact equation. What is it that I can do so that I don't have to, go, oh shit. what is it that I have to do so that I do not have to go through the, okay, I can't find the first derivative, I'll just give up. Surely there's another way, right? If I just simply wait. So instead of saying that, okay, I can't find the first derivative, but I'm going to focus, if I draw the graph again, I necessarily don't need the first derivative finding or whatever. You see, I have this section of the curve, right? I have this section of the curve and this section of the curve, don't I? I have two sections of the curve. So I'm going to call them minus epsilon and I'm going to call them plus epsilon, right? Now if I cannot integrate, because if I were to integrate, what do I mean by integrate? Integrate is adding each of the infinitesimal values or the infinitesimal positions. I'm going to integrate this guy here, I'm going to integrate this guy here, I'm going to integrate this guy here, I'm going to integrate this guy here. But if I integrate everything, this section is also included, right? This section is also included. So it's infinite. So if I integrate it, I'm going to do minus infinite plus infinite psi of x squared dx, I end up infinite, right? Because it's like 0 plus 0 plus 0 plus 0 plus 0 plus infinite. So it's 0, all of them 0 plus infinite plus all of them 0. So it's infinite. Right? It's kind of like that. Because the infinitesimal position here is 0, infinitesimal position here is 0, infinitesimal position here is 0, and so on and so forth. So it ends up all 0. And in the middle it's infinite, and then all of them at 0. What exactly can I do? How can I avoid this here? How can I avoid this getting the infinite value here? Exclude this guy altogether. I am going to get infinite regardless. Exclude it. What I'm going to do is I am going to write minus epsilon to plus epsilon. Because it's a finite, I am not going to focus on minus infinite to plus infinite like I would focus on an infinite square well. It's a finite square well plus there is a finite value. And there is a finite value. I don't know the finite value, but I held it as epsilon. I'm not going to say A or B or C, no, epsilon. Now minus epsilon to plus epsilon psi of x squared dx, this will give me 0. Why? Because whatever the value I have from 0 to the right and whatever I have from 0 to the left is the same. Sorry. Whatever I have for this value and whatever I have for this value, they are the same. It's like a symmetry. Like whatever the value I'm going to get for this, whatever equation or notation I'm going to get for this half of the section, same would go for this half of the section here. And so the difference between them will be 0. Now, that is why they're continuous. They're forced to be continuous. The only reason they're continuous, they're forced to be continuous, is this reason here. So that the left-hand side of the curve, so meaning this section of the curve, which is 0 from the left, and this section of the curve, which is 0 from the right, are equal. They have the same equation. Regardless, they have the same equation. So whatever the equation I'm going to use here, same equation I'm going to use here. Whatever equation I get here, same equation I'm going to get here. In that way, I can only use that differential equation that I get through integration, and I'm going to use that continuously. Maybe I'm going to find amplitude. Maybe I'm going to find position. The only reason is that if I were to include this guy too, then I'm going to get infinite. And now I would have to integrate infinite. Now your question may be, what if this was different from this guy here? Now sure. Now let's say this half of the equation was different. This half of the equation was different. So equation 2, equation 1. So equation 1 was not equal to equation 2. Right? So let's say that was the case. If equation 1 was equivalent to equation 2, I would get a 0. right? Outget is 0. So there will be no meshups, no ambiguity, nothing, no complex equations. So the only thing I'm going to get is that. That's it. Now let's say they were two different equations. If there were two different equations, I'm going to get one here going up and one down. For the same point, I'm going to get two different equations. So it will be like that, and it will be like that. So and that's the first derivative. Keep in mind, that's the first derivative. Now this is for the negative 0, and this is for the positive 0. Which means for the second derivative too, I'm going to get two different equations. Why would I have two different equations? Right? If I were to have two different equations, then I have to ensure that both equations correlate. But in no way, shape, or form, if I get two different second order differential equations, no way they're going to correlate. No way. It's not going to happen. The only way they're going to correlate is if my first differential equation correlates. And if the only way my first differential equation will correlate is if my original equation correlates. And the only way we can actually say, okay, this correlates is if this half of the section, whatever the equation is equivalent to this half of the section, excluding that x is equal to 0. I'm not saying exclude means exclude completely, but because x equals 0 is infinite, I don't have to use that. I don't have to get my final solution for pointing at that. I can use this half of the section, this half of the section, and I'll still get my final value. Cool. So that is kind of literally the entire lecture of bound state. We're going to do stationary state, a scattered state next, and I am extremely thirsty.